All right, recording. I have your tests. You can get them back at the end of class. Just come up, give me your name, I'll give you your test. All the grades are put into Blackboard and Hawks, so your grades are updated there, so you can get a general idea. If you use Blackboard as the more accurate representation of what your grade is right now than Hawks, because you have the chapter 6 or 8 test that's still there that you haven't taken, so that's going to lower your grade a little bit on Hawks. The chapter 6 or 8 test is already up online and Hawks and ready to go. I put it up there yesterday, so I know some of you already started going through and doing it. It does give you the option to upload your work if you would like partial credit for questions that you possibly got wrong. Work is important because I can look at your work and figure out where you made your mistake and see if it was just a stupid little mistake or if it was a conceptual error. The stupid little mistake, I give you most of the points because we all make them, including me. If it's you really didn't understand what was going on in the problem, you probably won't get many points from it. So, but it can't hurt you. It's only going to be able to help you. So you do have that option of being able to upload your work. You do not have to though. It's not like it's a requirement or anything else for you to do it, but you do have that option there. I think it's 10. I typically do 10. 10 seems like a good number. So,
when do we have to have it in by?
Friday at 11:59 p.m.
Question 1 has A to E.
Yeah, there's parts. So there's 24 total parts, I believe, on the test, if I remember right. So each part's worth like 4 points. So the questions that don't have more parts are worth more points on that one. Now, on the test that I just corrected, each question was worth 10 points. So it's just the way Hawks does that side of it. I think I gave you 2 hours to complete the test on Hawks. I believe you can pause it. So it won't, like if you stop it, the timer won't keep running. So if you don't finish it when you started it, you can go back to it and finish it afterwards. That's fine. Oh, I know I have. They did come in. So if you would like some of the sticky notes with the these, you won't need them for tonight's class actually. So before you leave, when you come grab your test, just tell me and I can give you some. So I've got 8 of them. So like split them into thirds or whatever else, and I'll have enough for everybody. So Amazon actually delivered things on time today. How about that? I think it got delivered to my house at like 3 o'clock, and I'm like, yay, perfect timing. So I think other than that, any other questions on what's going on? I'll have the nice thing about the Hawks test is once it's graded, you have the grade for it, unless I look at your work and I give you grade won't go down from that. It could only go up. So I'll put that over into Blackboard and put over the homework assignments that were due from 6, 7, and 8 into Blackboard. So I put in the ones from chapters 1 through 4 today. So as long as you had done them already, those are all grades are in there. If you hadn't, that's fine. You have to August 8th to finish those. Okay, so as long as you've completed the assignment, so Hawk says it's a check mark, it's 100. All right, so it doesn't matter what, like, because I think as long as you mastered it, I think a mastery in Hawks is 80%. It just gives me a check or a minus. So if it's a check mark, it's 100 in terms of what I'm putting in a Blackboard. So don't go back and have to do it a million times. Once you've mastered it, you've mastered it. So, all right. Yeah, I should put all the grades in. I'm probably on Monday or Tuesday next week for those. All right. So chapter 9. So I really actually like the example they gave, so I'm going to use it. Think back to the last time. Think back to the very first time you got into the bathtub yourself. Long time ago. If it was too hot, you like, because first thing you do is you turn off hot water. It's like it's too hot. You jump in, you jump. It's like it burns. So the next time you do it, you stick your finger in it. It's like, wait, let's see if it's hot. Did you do the entire tub? No, you did like 1 or 2 spots, right? So when you tested it, you didn't test the whole tub, you tested a sample. Where you test it will change what the temperature of the tub is. The closer to the faucet, the warmer it is. The further away, the colder it is. So if you were just going to take a sample and test it, depending on how you took that sample, depends on what you're going to end up getting. Okay. So what we're going to look at tonight is some ways to take those samples and how to do them, and then some ways that we can take a bunch of samples and use that data to actually have even a better understanding of what's going on in the population. Okay. So that's what we're looking at today. All right. I just really thought that example was kind of cute because it's like, oh yeah, we've all done it. It's like everyone did it at some point. All right. Here's a plane that came back from World War II. All the red dots are bullet holes. It survived. It landed. The pilots were alive when it landed. What would be your determination on how you would fix the planes so that the pilots are safer? Huh? Well, no, but I mean, in terms of the other, yes, you would probably not send it back out in this plane, but in terms of the other planes that you have so that they're safer when they go up.
Bigger steels.
Thicker steel where? So, give me my pen. So like here, put more steel around these areas.
Yeah.
They're getting shot up. Okay. You just killed the pilot.
The weight.
No. This plane came back. Right?
So how come they're shooting there and not like north?
This plane came back. What about the planes that didn't come back?
Those were the ones for the end.
Right. Those are the ones that were shot here, here, where the engines and stuff were, or where the pilot was. That's where they were shot. Those planes went down. Okay. So you wouldn't want to reinforce where the bullet holes are. You want to reinforce the other spots because that's where the bullets went through and the plane didn't come back. Okay. We have a, one of the things that happens quite often is something known as survivor bias. When you look at a situation, you look at it from your perspective. And if you survive something, you must assume you did something right to survive it and somebody else didn't. So do whatever you did multiple times and it's like, that's great. Well, maybe not. Maybe you just literally got lucky and they didn't hit the right spot. If you look at the other side of it, you'll get more information. That's why they don't look at the planes that landed correctly to figure things out. They look at the planes that crashed to solve problems because that's where the errors came up and that's where the problems are. So that's known as survivor's bias, which is one of the things. So we have lots of biases. Okay, no matter what we do, you are never going to eliminate bias completely. When you're looking at being able to decide things, you want to be able to understand the bias and try to eliminate as much of it as possible towards it. And whatever's there, making sure that the audience that you're talking to about your data understands what your biases are to begin with. Okay. So you have, when you're picking samples, selection bias is when you are either overrepresenting or underrepresenting some segments of the population. Okay. So whenever you have a bias sample, selection bias or anything, I'll put it up there in a second so you can write it down. It is where you're overrepresenting or underrepresenting some segments of the population. So when you look at data for standardized tests now, and like the SAT data or the CAP data when it came out or Smarter Balance or whatever, any of those nationwide standardized test that people take, you will see not only all the data represented, like the whole population or the whole school represented, you'll also see every segment of the population represented. So you'll see it broken down by ethnicity, you'll see it broken down by sex, you'll see it broken down by economic status. Because what they don't want is they don't want certain segments to start falling away. So if you have a school that's predominantly economically advantaged and people are doing really, really well, their scores might be very high. However, if they have a group of students that are economically disadvantaged and you look at their scores might be really low, but their total score is going to overwhelm that other one that's hidden there. So by just looking at the total, you're going to miss things that could possibly be going wrong in those type of situations. And what ends up happening is a lot of times, if you are a member of that population, you'll start to look towards that. If you're not, you won't. And that's where that selection bias comes into it. It's like, well, this number works out really well. It's like, well, yeah, but if you look at this, this, and this, something's going wrong here. So that's where that selection bias stuff comes into play. When you're looking at it, you want to look at the whole picture, not just individual pictures. This is where we get into how you can lie with statistics, because when you start to be able to cherry pick the data that you want to look at and that you want to focus on, that's where you can start to influence people's opinions and people's information that they're getting out of it. Okay. So how do we actually choose a better sample? So one of the things that we need to do before we can actually start choosing a sample is we need to define what's known as the sampling frame. Actually, I might put this on the other slide. So the sampling frame identifies all members of the population. And when you identify all members of the population, you want to identify what characteristics of that population could impact what you're looking at. Okay, so if we're looking at the number of cats somebody owns, we're probably like looking at different ethnicities and stuff like that's probably not going to make a huge difference in the outcome. Okay. But if we're looking at what type of car somebody buys, looking at their economic status might have some impact there. Okay.
What was it that you said before you didn't want to?
You want to, the sampling frame is looking at all members of the population, and you want to look at what pieces of that, what characteristics of that population would impact your study. So, how would you go about finding a randomized or a random sample? How would you do it? What are some ways you think you could do it? Yeah.
Have a list of the options and then randomly, like, have like pick from a hat or something like that.
Okay, you could put all the names in a hat and randomly pick out some names. That could work. How would you make sure that you fit the characteristics, though, the correct number of each characteristic?
Characteristics would be like
Could be anything.
economic status.
Yeah, it could be economic status, it could be ethnicity, it could be gender, it could be height, it could be like, it could be anything. It depends on what you're talking about. If I'm looking at the probability of people going into the NBA, height's going to be an aspect of that. So like height wouldn't be an aspect if you're talking about how much food somebody has at their house. Like that necessarily wouldn't be an issue, but it would be in terms of the other one. So that's why you can't say these are the characteristics you always want to look at, because it's not always going to be the exact same thing. So if you're going to randomly pick out of a hat, how would you do that? Okay. Yep. Then how would you, once you got the list, how would you actually use the random hat idea? Or would you change the random hat idea? Yeah.
You could get like different samples from like different like wealthy areas and not wealthy areas.
Okay.
Are you trying to get a sample where like the different groups are represented? Like,
Yeah, like,
groups
So you want the groups to be represented as well as they are in the population. You want your sample to be a representative sample of this
there's
population.
more of some group than other one.
You want more of that group in the population, in the actual sample. Absolutely.
You have to like.
Mm-hmm. Yep. So you can see how this would be difficult. This is not always the easiest thing in the world to do. So one of the ways that we can do it is actually very similar to the hat idea. It's called a simple random sample. So a simple random sample is where every possible sample, so you're basically picking out a group of people to make that study. So from a finite population, it's one where every possible sample of size n has the same probability of being selected. So in this case, we're not looking at characteristics. We're just saying everybody has the exact same chance of being chosen. Okay. That could lead to an over abundance of one particular group. However, this is where something we're going to talk about a little bit later is going to solve that problem. Writing names on a piece of paper and throwing them in a hat, that works. Typically, depending on how you're going to do it, you're not going to actually have everybody put their names on a piece of paper and throw it in a hat. Probably not going to work out for very large groups. What they will do a lot of times is they'll use a random number table. They'll assign everybody a number. Everybody in this classroom has a number assigned to them. Actually, multiple numbers assigned to them. You have your student ID, which is a number. You have your social security number, which is a number. If you have an ID or a driver's license, that's another number. Okay, so everybody has these numbers assigned to them. These numbers can all be thrown into a computer and random ones picked out. Because the number doesn't have anything attached to it that says who you are once that numbers are all dumped, that can be considered a random sample because there's nothing attached to it. So like once they pick out the 20 numbers, then they will go back and look at those and say, okay, these are the 20 people we're talking to. Okay. So that's actually one of the reasons everything's in numerical form. It makes it really easy for computers to be able to pick these things out and to anonymize your data, actually. So random samplings work fine. I'm skipping to 9.5. We're going to go back. Another one. Systematic sample. Ever play the game Duck, Duck, Goose? That's a systematic sample. If every third person's a goose, every third person you pick, that's systematic. Okay. So this happens a lot of times when people are doing surveys and stuff when they're walking around neighborhoods. They're supposed to go to every third house and knock on their door, or every fifth house and knock on their door. So a systematic sample is where you're starting at one point and then every so many after that point is what you're going to choose. So if I took all of your ID numbers, put them in a list, and I said I'm going to start at the 52nd one, and then I'm going to choose every 20th number after that point, that's a systematic sample. Is it still random?
Yeah.
Yeah, because the numbers were assigned randomly, right? Your ID numbers weren't put in order. Like there was no reason that you have your ID number and she has her ID number. So since they are typically still in a randomized order, it's still a random sample. Right? It just makes it a little bit easier sometimes to find them. speaking of numbers, everybody has a social security number. Do you know what it means? So yes, so you have 3 digits, 2 digits, and 4 digits, right? Okay. The 2 digits in the middle is the 2 digits of your birth year, or a random number based on that birth year. Because like mine's 82, but I wasn't born in 82. But there's a reason I wasn't born in 82. When I got my social security number, they weren't given out at birth. You didn't get them until you were 5 years old. I was born in 77. So I got mine in 82. If you look at yours, most likely those middle 2 digits are the year you were born. They're not. What's yours? Not just the 2. I don't want the whole social security number. Just
Mine's 08.
08. And what year were you born?
04.
Okay. So again, you probably weren't assigned it at birth. Yeah, and that's the thing. Yeah. That's the thing. It's like it's when it's not always when it, but that's the year you got your social security number. Is what it is.
Pretty sure we did that.
What month were you born in? You were born in September and your birthday. That's weird.
Mine is 02.
That's weird.
September 2005.
I was gonna say if it's 04 and not 05. Strange.
Yeah.
I think the probability that you're wrong here is pretty high.
I guess. Hey, you know what? I'm literally reading it right from the Social Security Administration. So apparently they have it wrong. There you go. Social Security Administration. I'm literally reading it right there. 9-digit number, 2-digit year of birth. Indicate. So that's like, it might be off. Maybe it's.
Wasn't there like an immigration factor to it though? Like,
Well, yeah. So it's not necessarily when you're born. It's when you get it. So because it's not those numbers are always when you get the social security number, not necessarily when you were born.
isn't there like a group of numbers reserved for those who are like naturalized or like whose parents are not born in the same? Like, there's like a group of numbers.
Maybe. So, well, the 3 digits, according to this, now that we're blowing it all out of the water, the 3 digits indicate where you were, like the geographical region. So that's supposed to be about where you were born or the region of where you were born, not necessarily the exact state. Again, when you get your social security number, it's because that's what not everybody always gets it right away. The last 4 digits is actually just random.
No, it says the current social security number is first through the area number, next through the group
Area
number.
group number.
So it's not.
Where?
As a result of the June 1936 decision.
Oh, yeah.
Area number, group
And
number.
what's
Yeah, the 3 digits is the geographic area right number. We don't use these anymore.
Deconstructing the social service.
So that's why mine is so fast.
Oh, those were okay. That's I was reading the wrong spot. There you go. Okay, now at least we're not.
From 1 to 10,000.
Yeah. Okay, so I'm not totally off on there. I just read the wrong section. And there's the beginning numbers. Mm-hmm.
Oh.
Wow. I guess that could be a good thing. So, assigning social security is issued card. Essentially, the area number has been assigned based on zip code of the mailing address provided on the application of the original social security card. That's interesting. They must do something with the zip code because the zip code is 6 digits or 5 digits, not 3.
That kind of makes sense. If I can do it mine. That makes
So-
sense on mine in my area.
I didn't even know the area code where I was born.
So here's an interesting question though. We were sitting here talking about how numbers, huh?
Someone can just like,
Someone can literally.
That's probably good.
that's wild.
Okay, so first of all, the whole concept of your social security number takes care of everything is so false, it's not even funny. Like, if somebody knows the social security number, that one piece of information does not give them the ability to steal your identity. It's they need a lot more information than is that. But we're talking about how numbers are randomized, and like your student ID, there's nothing attached to it that student ID, and so you go back and look at what that student ID in your file, where your social security number is not completely randomized. So using the social security number, the first 5 digits actually will give you information about the people that you're talking to. Okay, you can easily figure out like what year range they were born or where they're from, those type of things. So you can find that information out based on that. That's why a lot of times when they ask you, they only ask you last 4. The last 4 is random, so that this way they actually do use that information. So interesting things we learned. All right. Next one. Actually, hold on. Where is... Next one is cluster sampling. So cluster sampling is dividing the population into clusters. The cluster is used when there's natural groupings in the population. So let's say I wanted to do a survey of the school, of this college. And no, it will not work right now, but imagine this was like 11 o'clock during the actual fall semester on like Tuesdays or something like that. So there's a bunch of people in the building. What would be a good way to cluster the students at that time? It would be a natural grouping that's already there and evident in the population.
Oh, yeah.
Okay. We could, but if you, so remember, the whole point when we're looking at random samples, we still want to get a representative sample, right? So if we just took the males or just took the females, we wouldn't have a representative sample of the group, of the school, right? Same thing with freshmen and sophomores or first year, second, whatever year we want to do it. That still wouldn't necessarily give you a representative sample of the entire population. Huh?
Major?
Okay. GPA major is a little better. Age range are going to fall in the same group as like the classes and stuff. Or
I won't be able to do that in the daytime. Have to be an evening.
yeah. Okay, so yeah, so even if I did it at 11 o'clock, I probably wouldn't get a completely representative sample because I'd be missing a lot of people that were working for it. So yes, this is very true. Okay, we're thinking clusters wrong. But that's okay. No, that's fine because I didn't tell you what a cluster was. So totally acceptable to think about it wrong. Classrooms would be a cluster. If I went through and I picked one classroom in every hallway, like every section, like you pick one classroom over here, one classroom over there, one classroom, like that would be a cluster. And in each classroom, I would typically have a more randomized sample of the population. I'd have a mix of male and female. I'd have a mix of different grade levels. I'd have a mix of a lot of things. Okay. So when you come into a school, the classes are a natural cluster, already a natural grouping that are evident. Okay. If this was in a high school and I looked at the classroom, everybody in his classrooms are pretty much mixed up. So I would get that natural grouping. Why would that be more beneficial to do a survey that way? Because then I could just go to the teacher and say, okay, I'm just going to walk down and hand the teacher in each of like a random rooms. Here's the surveys for your class to take. Come pick it up. It makes it a lot easier than sitting in the hallway trying to get people or randomly selecting 100 people throughout the building and have to go find them and stuff. So that cluster makes it simpler to do.
At the end of the semester.
No, they do it at the end of the semester so they get a better understanding of what the teacher did. If they did it at the beginning of the semester or anything else, you wouldn't really have an overall view of what that teacher did. That's why they do it at the end of the semester. And we don't find out for like months after you fill them out. And when it comes up, please fill it out. And as not even that it doesn't go against me if you don't or not. I actually read them, and I do make changes based on what I hear. Unless I hear the exact, I heard when the surveys, I had a few students say they wanted more homework because they didn't feel like they had enough homework in the class. And then I had other students in the same class say the homework was fine or we want less homework. And I'm like, I can't do both. I'm like,
So no changes can happen.
so that change is going to happen as well. But no, I actually do read the results and I do make changes based on things if I feel that there's something that does need to actually be changed. So, so if we're cluster sampling, it just makes it more, it's more convenient to do it that way. Now think about if you're going out and canvassing a neighbor or a city to find out what the people are looking at in terms of voting. Is it easy for you to go to every single house? No. So what would be the natural clusters that we'd want to do in that situation? What is a natural way that people are clustered in a city or a town? Neighborhoods or even blocks, right? Depending on where you're at. Like, so I can drop people off and say, okay, you're going to walk around this entire block and have every single house on this block. That's a cluster. Okay. So I can easily do it in that way and still get it. Now, the one big piece of information in there is the cluster still has to be determined randomly. Okay. I still want to randomly select those blocks. So there's still got to be some kind of randomness involved into it. It can't be, I'm just going to ask the first 5 blocks I go to, I'm good. Like that's not, that goes back to that convenience factor and that's not good. So you still want to have some randomization there. What's a problem with if we just do the clustering though? Are we still going, are we going to, so remember I said at the beginning, we were talking about biases and we want to make sure that we hit all the populations and everything else. Are the methods that we talked about, are they going to be able to do that? So like is a systematic sample or the random sample we talked about going to be able to get all the different groupings that we might want? Is the cluster sample going to be able to get those groupings? Is the cluster sample better than the random samples that I did before in trying to get those groupings? Or is it about the same? Okay. Cluster's a little better. Nope, still got to do random.
So this is more convenient.
Still got to do random.
That's why you want to do a cluster.
The cluster makes it more convenient because you have a group of population there. And as long as the clusters are generally randomized, like a class, like if I'm picking classrooms, those are a little more randomized. You're right, I might not get the right age groups depending on when I'm going to take the survey, but I might deal with that and say, okay, I'm going to do 10 classrooms at 11 o'clock, 10 classrooms at 3 o'clock, and 10 classrooms at 7 o'clock. So I can hit those groups. Now I have 30, they're still clustered, it's still there, but I'm going to get that piece there. But now actually moving into a more set up version of the clustered sample, which is known as stratified sampling. So because we want to have that different areas in there, stratified sampling takes those identifiable characteristics. So if I want to make sure that I hit the age ranges and the different types of students that come here, asking at different times are going to hit those different aspects of it. So I'm going to get that older population, I'm going to get the younger population, I'm going to get the commuters, I'm going to get the people who are coming full time as compared to the ones who are working full time. I'm going to hit those different groups by doing it at different times. That's a way that I can use it as a stratified. Another one, a way I can do it is if we're looking at, say, neighborhoods in a town. If I randomly pick blocks, I might pick them, and they all might end up being more affluent than the town is. If I know that the town has certain neighborhoods that are a little less affluent and more affluent, I might want to make sure I pick certain blocks in those areas. That would go away from that randomized concept. But as long as we randomize inside those strata, we're still good. So as long as I randomly pick up the blocks in certain areas and randomly pick the blocks in the other areas, I still hit that clustered factor. It's still randomized, but now I'm making sure that I hit those characteristics that I want. Does that make sense? Yes.
so like the, I mean, the proportions, the size of the strata, the accurate size of it.
Correct. As close as you can get. Like you're never going to be perfect, but this is where all that census data and everything else that we have, where we collect data for the entire population, really comes into help. Because based on that, we can get a good understanding of where the neighborhoods, where the areas are, what is the population within that county or the state or the country or whatever else that we're looking at to be able to break those things down. When you guys apply here, you fill out, there's a whole questionnaire and everything else in the application, like you check off these a bunch of boxes and stuff to say what you are. The reason why is because that then puts you into groups that they can make sure that they pick certain areas out of there. So that when they're doing surveys and we're doing those studies, they get that general aspect of it. And when you do those surveys at the end of the class, those surveys all go in or anonymized and everything else. So we don't see who put them in, but they can then break that down by the school and say, okay, they're finding that students who took special ed services in high school are scoring teachers a lot lower on their surveys than students who are not. Okay. So what are we like? Is there something that they're falling down that now they can use that data to be able to figure those things out? Okay. So they have that information already built in. When you supply the surveys, then they can find out, use that to actually make some changes. So you can start to look at how a lot of the things that we're looking at when you're doing these types of studies is all the data and everything else you got out at the end only is as good as the stuff you put in at the beginning. You know, the concept garbage in, garbage out. If you have a crappy sample and don't do a very good sample study at the beginning, the data that you're going to get out isn't going to be useful. And you're going to be able to you're going to make wrong assumptions based on that data. So one of the things that I talk about all the time, like with social media and whatnot, is the social echo chamber. If you're looking at just what you're seeing on your social feeds, they're feeding you information that's going to get you to stay there. So they're going to give you information that makes you happy. So that's not a very good sample of what the entire population necessarily thinks. That's what the group that is like you thinks. So breaking out of that, you start to see a lot more of a wider view. And unfortunately, a lot of studies fall into that sample bias, that selection bias, or they pick things that are going to fit their criteria. Okay? So things to be careful of. All right. Now that we're done talking about how to get this information.
What was the example for the stratified?
I did it with the classrooms where I was making sure I picked classrooms at 11 o'clock, 3 o'clock, and 7 o'clock. So I can pick at different times. But the sample that they typically use is making sure you pick blocks. If you're going to do neighborhoods or blocks in a city, making sure you're picking from different areas so that you get the sample that's very similar to what the population of the entire town is. So if we're looking at New York, make sure you're picking in different boroughs. Make sure you pick a couple blocks from the Orthodox quarter. Make sure you pick a couple blocks from Chinatown, things like that. So you make sure you get a representative sample of the entire town. So you're never going to get everybody because that's impossible. You just want to make sure your sample is as close to representative as your population is. So this way your data is useful. So that's why if you ever get called up by a certain person that's doing surveys, the first questions they always ask you is exactly what they're talking about right here. What's your sex? What's your age? What's your income level? What's your political party? Like these are the questions they ask. Because when they actually go through and do all the questions, they want to make sure they have a certain number of people in all these different areas that are representative of the entire population of the United States. So this way they can use that data to have a general idea of what's going on in the whole country. All right. So we're back to the bathtub issue. Stick your finger in one spot, get a sample. Stick your finger in another spot, get a different sample. Are they going to be the same temperature? Probably not, right? So if you do that, like say 10 different times, you get a pretty, the more times you do it, the better, the more accurate you're going to have of that entire tub, right? So what we typically will do is you won't just do one study. You do a bunch of them. So we have, when you're selecting a bunch of them, what you do is you actually have what's called a sampling distribution. So a sampling distribution of a statistic is looking at the distribution of the means, which would be the average, or the median, depending on which way you're going to look at them. Most times we use the mean in these situations because it's easy for us to calculate it. And since we're doing a bunch of different samples, that makes our life a little bit easier. The sampling distribution statistic is when we take all the possible samples. So if I have 10,000 people and I'm taking samples of 50, this would be the mean of every 50 sample out of that 10,000 people. Okay. Remember, you're never going to do them all, but the more you do, the more accurate the information that you're going to get is going to be. When you're calculating it, the other piece of information we find is what's known as the point estimator. I know a bunch of definitions today, sorry. It's always a bunch of definitions at the beginning of the next section. So when you're doing your calculation, you want to get, the goal is to be able to estimate the population. Whatever you're doing, whenever we're doing any of this, our goal is to be able to figure out what the population is going to be. So when you're taking the point estimator, that's taking a single value, and that value should be as close to the population value as possible. Right? So if I asked, let's see, if I just asked this class of how many animals you have at home, and I got all your different, let's say this is a randomized sample and I got all the information for you guys. And I did my study and I was like, okay, this is how many animals is in the entire school. That'd be one thing. It'd probably be an okay estimate. But if I asked that of 15 different classrooms in here, so I took the mean of this classroom, the mean of those other 15 classrooms, and then I found the mean of all those, now I have even a better estimation of what the entire population is going to be. If I was to do that to every classroom, I'd have the exact answer, right? And what the interesting thing that comes out is that those means actually all make a nice bell curve. So it all ends up going back to what we did yesterday, or not yesterday, Monday, when we were talking about the.
Sorry, for this video, what I want to do is.
Oh, I'm like, what? Fine. I thought so. I was like, wait, what? The internet is crazy sometimes. So the goal of doing the concept of finding all the different means is because we want to try to get things to that bell curve. If we can get things to the bell curve, I can use my z-score, I can use all those tests and stuff that we did in chapter 8 to be able to figure out those answers. So that is our goal, is to always get back to the bell curve. So let's look at I'm just trying to figure out how I should want to write this section because I don't really like the way they did it. Come on. So an interesting thing happens. No matter what way the population is, it makes no difference how the population is distributed. If we take samples, okay, larger the better. And when they're talking about large, they're talking about like 50.
Like,
I know you think large, like, oh, thousands. No. They're talking, as long as it's over 30, technically it's large in terms of statistics, believe it or not. So when they're talking about taking samples, they're talking about like 50 to 100 people. Like, it doesn't have to be a massive number of people. If I took all those samples and I found the mean of every one of those samples, it would fall into a nice bell curve. There'd be about 50% of them that would be lower than the mean, about 50% of them that would be higher than the mean. There won't be, the outliers are going to be really low. It's going to fall into that. No matter how the population is distributed. If it's like bimodal, there's like peaks at either end, doesn't matter. Even exponential, where it's like all built in one side, if I took those means, again, the means are going to still fall out just like that. Even the normal population is going to be that, even if it's uniform, the mean is still going to fall into a nice bell curve, which sounds weird.
not for the same thing distribution.
Yeah.
But always, falls into a.
So as long as you're looking at a sample of means, so you're taking the mean of a bunch of different samples, you're going to get that nice bell curve.
That's for distribution.
Yep. The distribution of sample means. So the central limit theorem, this is the calculations and stuff we'll get to. We're going to start getting to in a minute. Remember I said 30? If a sufficiently large random sample, n is greater than 30. N is the number in that sample. So it does not have to be massive. Is drawn from a population with mean and standard deviation. The distribution of the sample mean will have the following characteristics: an approximate normal distribution, regardless of the distribution of the underlying population. So that's one of those situations where, remember, if we can't get it to be a nice bell curve, we can't do all that work that we did before. So by doing this kind of concept, we make it a bell curve. The mean of all those samples is actually equal to the mean of the population. Even if you don't know the mean of the population, when we find the mean of all these samples, we have the mean of the population. The big piece comes in this place. The standard deviation of this new distribution is equal to the standard deviation of the population divided by the square root of whatever the sample size is. So the square root of that sample size will always be larger than 1. So does that mean my standard deviation is getting larger or smaller? Smaller. Because if I'm dividing the standard deviation by a number bigger than 1, it's going to get smaller, right? Standard deviation that's smaller means what? 3. Is a smaller standard deviation, what's the smaller standard deviation tell me? It's more accurate. It's less variation, right? The smaller the standard deviation, the less variation we have. So if I'm doing this, I'm making my standard deviation smaller, which makes my variation smaller, which gives me a more accurate representation of what's going on. Okay. All right. Let's do some math. I'm done talking. Company fills bags, fertilizer for retail sale. The weight of the bags, this could be anything. I was trying to look for a cereal problem, but they didn't have that. The weight of the bags of fertilizer have a normal distribution with a mean weight of 15 pounds and a standard deviation of 1.7 pounds. What is the probability that a randomly selected bag of fertilizer will weigh between 14 and 16 pounds? Oh, if you guys want I lied. You can use these little things today. Would you like some?
Sure. Thank you.
Would you like some? Want one? Oh, okay. Oh, okay. Then take a few and use it. Would you like some? Would you like some?
Thank you.
Very well. You're welcome. All right. First question. We're looking at question A. Is it talking about the mean of, is it talking about sampling means like a bunch of things or just an individual bag? They're talking about an individual bag. So we're doing exactly what we just did in the last class in chapter 8. Okay. We're going to use the z-score and the z-table. So I need buffers. All right. So what's my mean? What's my standard deviation? Okay. Good. My X is going to be what? 14 and 16, right? We got to do both. All right. So how do I find my z-score? Yes. And the other one's going to be, oh, it's not 16, 15. What was it? Okay, so 2.9. No, I didn't do it. So.
0.59.
All right, hold on. Now that we got two different numbers, I got to take out my calculator. It's okay. 0.59. Oh. And this one's negative, and this one's actually positive. They're the same number. All right. So, and I'm looking at between those two, right? So 14 somewhere over here and 16 somewhere over here. So I'm looking at those. So I'm going to subtract the 16 score from the 14 score. So 0.59. What?
They cancel each other out. Is that what you're thinking? Both the 0.59?
No. I now have to find I have to go to the z-table and find the probability for each one. Yeah, that's the 16 one. Yeah. And that's that one. So now we're going to subtract those two. So the probability is 0.4448. At least for my numbers, that you're going to round differently on yours.
You said you subtracted.
Yeah, because I want to find the difference between them. I want to find the individual. Remember, they always go all the way over to the left. So by subtracting off this piece, basically, which is that, I get the piece that I want. So the probability that a randomly selected bag of fertilizer will weigh between 14 and 16 pounds is approximately 44.48%. Does that make sense? So that's just picking one bag. That's what we did on Monday's class. Now, so we have the same information, but this time we're picking 35 bags. So my mean was still 15 and my standard deviation was 1.7. But now we're choosing 35 bags. So now we're doing the sample means like what we did looking at today. So we've got to find, my mean is the same. Remember, mean doesn't change. Okay. If we didn't know our mean, we would use the mean they gave us for this sample, but they gave us the mean for the whole population. So we know that. The standard deviation does change though. So my standard deviation is now 1.70 divided by the square root of 35. Okay. So my standard deviation now is a lot lower. So now, what is the probability that the average weight of 35 bags will be between 14 and 16 pounds? We're going to do the exact same thing we just did. Right. Right. So we're going to do now, when we do the x equals 14, my z is going to be 14 minus 15 divided by, thank you, finally caught my screen, finally caught up. Divided by 0.287. And then the 15 one, same, or the 16 one. Same thing. $3.48. Yeah. That's the negative one, and this is the positive one. All right, so let's go look at what's 3.48 now. That's that one. Subtract those two. Yep. So the average weight of 35 bags will be between 14 and 16 pounds. It is almost 100%. Okay.
The average weight being in that range a lot higher than an individual one.
Correct. And that's the point. So remember, we were talking about how when they take samples out, they can use that to determine if they're going to reject a shipment or keep a shipment. If my pallets have 35 bags on them, I can weigh the pallet. So if the weight of the pallet is, let's see, hold on a second. If the weight of the pallet, say 480 pounds, I know it's not accurate, and I would reject it because that's way out. Like there's no chance that would be true unless the bags are severely underweight. Okay, because I have a 99% chance that they'd be between 14 and 16 pounds each. That make sense? So by taking the sample and looking at the sample, we get a much more accurate view of what's going on. And my standard deviation is a lot smaller, so therefore I get a lot more compressed view. Make sense? Okay.
Does it matter when you like do the assignments, which Z table you get your data? Because like you got 9995, but I'm on 9994.
Yeah, me too.
His goes to 5.
Yeah, mine's going to 5 places and yours isn't.
That's what I was confused about, because I went and looked at
So which one are you
Mine's
supposed to
point,
use?
I would.
Hawks use the Hawks one.
Okay, 4. But
Yeah.
Yeah.
And I think actually when you're doing the questions in,
Sometimes it gives you a.
they should give you a Z table there.
Like, yeah.
Yeah.
Like between Z and 0 and Z, and then.
Yeah.
Infinity.
Yeah. They should give you a Z table that you can look at right in the problems. I would use that because they're giving it to you, so that's what they're going to base their numbers off of. But a one that's now in the 10,000th place isn't making that big of a difference in the grand scheme of things. It will in terms of the answer that they want in the book, though. So use the book. All right.
If you get it right away, or you agree?
Nope, it'll tell you if you got it right away. So the score will never be lower than what you got. If you submit your work, I will look at that and I could increase your score. But what you get, that'll be the lowest possible score you can get. That was weird. All right. Well, I'm going to give you a little bit of information and then you guys are going to find the answers to this. So we're looking at the average of 50 scores. So what's the mean? So the mean is 75. What's the standard deviation? 12. What's the standard deviation of the mean of the 50? It's 12 divided by 50. Is 1 point, right? So 1.70 because you actually we can do 3 different places for this one. So 697. The Z score you can only do 2. All right. So find me the answers for A, B, and C. No, you can use 80.
Just the 80.
Yeah, you can use the exact number because they're not discrete values. We'll get to the point where we're doing those with the probability.
I saw at least.
When you're doing these problems, think about the numbers you're doing and save yourself work. What's the probability that the average score of 50 is at least 80? What are we doing for it? We're doing greater than 80, correct? So my Z is going to be 10, or not 10, sorry. 80 minus 75 divided by 1.697, right? So that's 10. It's 5. Which was, what was it? 2 point, so 95, because you can only look two decimal places. At most 70 is the exact same thing. It's the exact opposite. So it's the same thing you just see it here, except it's the negative 2.95. You don't have to redo the calculation again. Okay? Because at most 70 is just, it's 5 below, it's just going the other direction. And if you're looking at the little bell curves for it, what I wanted to do. Remember what we were talking about? That if 75 is in the middle, 80's here, 70's here, that part and that part are the exact same area because it's symmetrical, right? So if we're looking for the answer, what did I get? 0.00164. So this one right here is 0.00164. So this one right here is 0.00164. It's the exact same. So those first two questions, the answer was identical. And if you understand how the bell curve works and realize that it's symmetric, you only have to do it once. And then the other question was it 72 to 78? So 72, 78, and that ends up being 0.9216 in the middle. Because it's 0.9608 minus 0.0392. So if this is a test, right? So the water safety instructor exam, the average is 75, standard deviation of 12. So if I had a instructor who's gave this exam out and the average of his test was an 82, the average of all 50 of his students was an 82, is that normal? No. I'd be calling up and saying something happened in that class because this shouldn't happen. Okay. Ever see the movie Stand and Deliver? Stand and Deliver was Herman Escalante out in the East LA, and he gave a bunch of high school students calculus tests. He gave them the AP Calc exam. He trained them really well. They did exactly that problem. They did that. Their scores was so far above what should have happened that they assumed cheating. And they went into the school to check. Okay. So, and the opposite end would also be true. If the scores were if the average was well below a 70, something's up with that teacher. Something happened in that classroom. Either they didn't teach the material correctly, or again, something was going wrong because that shouldn't have happened either. Okay. So you can start to see how they use this type of information to determine what's going on in terms of materials, in terms of testing, in terms of lots of things. And that's how they can quickly determine if something is out of whack, because they already know all this information about that test. Okay. Huh? All right, so let's go through and how you got
I
it.
got it right, but I didn't.
I don't think I like somehow.
Like,
messed it up
I was
somehow.
like making like standard deviation right now.
Yeah, because they're both the 0.00164.
So how come you put like, you put 75 in the middle, well, you put 80 and 70, so just 70 or close. I mean, so.
Okay, so at least 70 is 80, at least 80 is 80 in grade.
Yeah.
Right.
Well, I marked like the standard deviation.
So in this case, the standard deviation doesn't change.
Yeah,
It's always divided by the square root of 50. So that's still 1.697. That stays. Oh, I didn't. No, I didn't. You're right. So your z-score is the peaks. That's the important part. So we did 80 minus 75, which is 5, divided by 1.697. And should be 2.95. Okay? So then you look at your bell curve.
Why would you look at the bell curve and not go straight to the floor?
No, you look at this, 2.9495. So I'm looking for 2.95.
Okay, yeah, 'cause you just get negative.
0,
So
1,
originally
2,
it's
3, 4, 5.
7,
So 99841.
Yeah.
Oh, I was off by a little. I was off by one.
Right.
Okay, I was.
So it's the same because that's the 70 minus 75.
Where's the negative version of it? 'Cause the negative version is going to be the right answer. 0, 1, 2, 3, 4. Oh, you know why? 0 is the first column of my list.
Yeah, I have to make myself hyper aware of that.
Yeah, 0 is the
Like
first.
0, 1.
So it's 00159 actually is the right answer. Five, 9.
Yeah, so 0, 0, 1.
Yeah, or 0016.
I feel, isn't the 8 one the positive?
Yeah. That's not negative. It's the decimal point.
Oh,
So for the 71, you wouldn't do 1 minus.
So for the 81, you would do 1 minus it.
For the 81.
Yeah, because the 81, when you look for 2.95 on the Z table, you're going to get 0, 1, 2, 3, 4, 5, 99841, which you then have to subtract it from 1 to get 00159. The 80? I made up a test score of 82 in my little example of if this average was an 82, something would be wrong.
I think what's
Can you
throwing
do
me off is what,
Yeah.
when do you know to subtract it from 1?
Yeah, because I.
That's where the bell curve piece comes in. That's where drawing out the curve comes in. Remember that this piece over here, I'm going to color it in a different color real quick. This piece over here, right, is what I want. That's greater than 80. Correct?
Oh, and that's.
But it's going to give you up to that.
Okay. So then
So
that's why
whenever
you
you see
start-
the term, the word greater than, you should automatically.
You're going to realize you're going to subtract. But that's why I gave you the bell curve. So when you draw it, mark what you're looking for. And remember this, they're always going to give you from the left all the way to whatever line it is. But that's why I was saying understanding what the bell curve works, how it works, will help you. Because if you did D first, which is why they didn't put it first, you would have gotten this answer here. Okay? Because again, it's from the left over to that point. Knowing that it's symmetric, you didn't even have to do this one. It's the same answer.
so is that 0.159%? Or is it?
Yes, 0.159%. So that's what I'm saying. Like if somebody got like an average of an 82 on the test was for the whole class was an average of an 82, something is wrong there. Like there was some cheating going on or something, because that should just never have happened. Okay. In this situation. C, you have two numbers. We had 72 and 78, right? So you're going to do, let me change back to my red. So we did X equals 72 and X equals 78. So you did 72 minus 75 over 1 point. Yeah. And then if you did 78 minus 75 over 1.697, it'll be the positive 1.77. Now we look at the bell curve or the table for that. 0, 1, 2, 3, 4, 5, 6, 7. So the positive one is 96164. That's the positive one. And the because I'm going to write it so I can just subtract it underneath it. And the negative one was okay. 0.0384. And we subtract those two, and it's probably going to come out because I think I counted wrong too.
How many decimal places should we represent? 2, 3, or 4, 3?
3 is fine.
the space between 72 and 78.
0.923. I really hate that they put the 0 first.
Question, when we're given at least 80, you should kind of always find, like, I
Yes,
think, so at least you always want to subtract it.
right, because you're going above it.
And then
You leave it because you're looking at the left. So it depends on what, at most means you're looking at the left side of it. At least means you're looking at the right side of it. Since it's the right side, we have to subtract from 1 because it starts from the left.
I thought you said greater than was subtraction.
Yes, which is the exact same thing as saying at least.
Because if it's at least 80, then you have 80 if you want 82.
Right, it's greater than 80.
So at least you subtract the 1, and then at most you just leave it like this.
Gotta love English.
It's
Greater
that,
than,
it's not
but
even
like
like
if it says greater than you.
Oh, no, you don't have to worry. Yeah, so greater than you're still subtracting 1 because you're still going up. So at least and greater than mean the exact same thing. They're both subtract 1 because they're both on the right side. At most and less than mean the exact same thing. They're both on the left. You can leave them alone. Yes.
I was a little confused on the chapter 8 stuff when it would say, it would be like, what's the probability that whatever lies to the left or to the right? Is that the same thing? Like if it's to the left, you'll subtract.
If it's to the left, you're not worrying about it because it's to the left.
it's to the right.
It's the right you subtract.
That stuff was messing me up.
Yeah,
I
just
couldn't,
the curve.
I couldn't do the area under the curve stuff even though we did it and I had an understanding of it.
So it's the same thing you're doing right here. This is literally the same thing. If they're saying to the left, you don't have to worry about subtracting 1 because the number you're getting is to the left of that number. To the right, you have to subtract 1 because you're going the other direction.
If they give you the area under the curve and they're asking to see.
You go backwards. You go backwards. If they're giving you the probability, that's the one you have to go backwards. So you have to take that number, find the z-score in the table, and then use that to find the x. That was the one that we did the little algebra last class.
For it, they divide one.
That one is messing me up. I can't wrap my head around
That was the algebra. All right. P-hat. All right. So we actually talked about this a second ago. We were talking about when you were asking, do you have to do the subtraction and stuff like that? As they were discrete. A lot of those times when we were looking at those, we were typically looking at probabilities. So we're looking at like the proportions. You don't necessarily have to worry about that in terms of what we're doing here, because we're looking at means, which is continuous. So we kind of eliminate that piece, which is kind of nice. So just like we were looking at before in last class in chapter 8, when we were looking at proportions, same concept still happens that we just talked about doing a sample of the means. So if I'm looking at a proportion, I'm doing sampling of a groups of population, and I find the means of those or the proportion of those, I can compare that the same way that I just did the median problem. Those are p-hats. So p-hat is the probability or the proportion of the sample. Okay. put that in the notes this way. There you go. P hat. And you find it the same way. It's just the number that you wanted over the number that you sampled. It's just the proportion of the sample, not the proportion of the entire population. Now, just like mean, the mean of the proportion, the sample proportions is the same as the proportion of the entire population. So that doesn't change. We don't have to worry about changing that. The thing that changes again is our standard deviation. So if you remember our standard deviation before, it was the number that I had times the proportion times the 1 minus the proportion. The difference in this case is we're dividing by the sample size. So we're dividing by n. So my standard deviation is this piece here, where it's the same concept. It's just the proportion that I want and 1 minus that proportion, and it's divided by whatever my sample size is. I'm going to age myself. Has anybody ever here done the Coke Pepsi challenge? Try to determine if you know which one's which.
Oh. Yeah.
Pepsi has citric acid in it. That's actually the only difference.
Really?
That's what makes the taste a little different, is the citric acid. And you know, Pepsi is not the third most popular Coke or cola anymore. Dr. Pepper's number 2. Dr. Pepper's number 2 now. Coke's still way far ahead of number 1. All right. I'll go back. It's fine. As soon as I clicked it, I heard the groans, and I'm like, they weren't done writing yet. Excellent. So ignore the bottom. Don't worry about. The bottom is exactly what we've already talked about. It's going to make total sense when you see it.
I mean, we've already been using n.
It's just so all the proportion is, think about it. When you're looking for a probability of something, you take the number of successes divided by however many total you had, right? That's all that is. That's literally what X over N stands for. It's the exact same thing. Okay, so don't get totally confused by that. P hat means the same thing. It's just it's the proportion of the sample, not the entire population. So we have to mark it differently. And that's what the hat stands for, huh?
Can you move it up a little?
Oh, actually, I'll do it this way. There. So yeah, don't get totally confused by P hat is the exact same thing we were doing before. We were looking for proportions and probability. Yeah. He has a little hat. I actually don't remember what the name of that symbol is. There's actually a real name for it.
You have to name everything.
The funny part about it is typing P hat into Google, it comes up exactly that. Or the carrot. But there's got to be because it's used in other languages as like an accent character, and it's like, so I know there's an actual like language-based name for it, not hat, but mathematicians are lazy, so it's a hat.
Yeah.
All right, let's play Pepsi and Coke. Actually, hold on a second. Let's see. It's funny. I type it. What's the percent of population that prefers Pepsi? Because I'm trying to find like actual like number, like if they have the data now, and all I find is the answers to this question.
Oh,
Not the question I want. All right. So the latest study that I can find says only 1 in 3 people prefer Pepsi to Coke. Yeah. Out of 36,000 respondents worldwide.
Is that what they ask people? Or-
Oh, I don't think it's a blind test. If there was an actual study that did this, I would question the results purely because it was probably paid for by Coke or Pepsi.
yeah.
So, all right, so we'll do that. We'll go with the number they got because even though I know it's not 50-50. If the true population prefers Pepsi is really 50%, what's the probability that less than 0.44 of the persons in the sample will prefer Pepsi? So, let's pull our information out. When we're looking at this information before, what do we need? We needed 2 pieces of information, right? We needed N and we needed P. So in this case, my N is 400 and my P is 0.5. My P hat is 0.44. That's what I'm testing. Well, actually, yeah, that would be hat. Yes, never mind. All right. So when we did our thing, same concept we did before. My mean. So we're looking at this. It's just the proportion. So in this case, it's just 0.5. Okay. So that is my mean is 0.5. Standard deviation, we have to do a calculation for. So that's my
So we're doing standard deviation for and I'm looking well,
no, just the standard deviation. We have the population standard deviation. We have the population percent, so we use that. If you didn't, then we would use the other one. So 0.025. This is 0.25 divided by 400.
0.025.
Yeah. Hold on. Hold on a second. 0.5 times 0.5. So we're doing 0.5 times 0.5, which is 0.25 divided by 400, and then the square root of that. 0.025. Make sure you're using parentheses. Huh? Yeah. Yeah, you didn't do the square root. Do the square root of that number. That's what you get before you do the square root.
but it's not 0.25.
It is 0.25 divided by 400, which gives you that.
I got that.
Yeah, we're good. All right, we're good. Let's find my Z now. So we want less than 0.44, so we want to the left, so we're good. We don't have to do any subtraction or anything else like that. So we want that p hat is less than 0.44. So we're going to do, so my z is 0.44 minus 0.5 over which is negative 2.4. So if we go to negative 0.24 on my table, 0.0082. So the chances, no, it's, yeah, 0.82%. So if I did a survey and I got my probability of, say, 40% is there, we can make, the thing about this one is you can make one of two assumptions. One, that your survey wasn't very good. So you'd redo your survey and see if you get the same type of information. If you continue to get those, though, what you're going to make the determination is that if the population really doesn't prefer Pepsi at 50%, that number is too high. It's lower than that. So that's the other way that we can look at the data. So when we looked at the test scores, we said, well, if they scored an 82, that's impossible based on the information they got. So, and we would assume based on that test that they have data from hundreds and hundreds of examinations, and they know that information is pretty accurate. So we wouldn't make the assumption that their information is inaccurate. We would make the assumption that something about the test is inaccurate. And this problem right here, though, when we did it, it says if the true fraction of the population prefers Pepsi is really 0.5, so that's the piece that they're not sure on. So if it's really 0.5, what would be the case? Well, if it was really 0.5, the chances of what my survey came up with when I looked at 400 people wouldn't happen. So my assumption would be at that point, it's not really 0.5.
It's less.
It's less than that.
Did you get 82% of that?
I got 0.82%.
Oh,
It's okay.
Yeah.
The wonderful decimal points.
I didn't see that decimal point either, so I just was like, oh, that's totally easy.
Wonderful decimal points. So. All right. I think we're good. So we're asking before, like, what's the final going to be on? And I said, it's going to be cumulative, but if you think about like what we did tonight, we did a bunch of stuff from chapter 8 and chapter 9. And when we're doing chapter 10, it's going to be a combination of a lot of other things. So it's going to be a lot more of the end stuff because it kind of flows together in situations.
How many questions on that one?
15. Hopefully. In all honesty, it really depends on how long it takes me to cover chapter 12 on the Monday before the final. Okay? If I get through chapter 12 at a decent time, we'll go through a little bit of a review for the final exam. If it's 8:30, 9 o'clock when I get through chapter 12, probably not going to have a chance to do a review for the final. You will have 4 hours to do the final. I do not expect it to take you 4 hours.
Will there be a review possibly on the thing?
Yeah, if I don't get a chance, I will have a review for the final on Hawks because that will be in person. So I will have a review on Hawks for you of similar files like I did for the chapter 1 through 4 test.
Finals online?
No, it's in person. Yeah, it's in person.
We have 4 hours.
Well, yeah, because technically you have 4 hours every night of class.
Oh, yeah.
Technically, class goes from 5:30 to 9:30. I've not kept you till 9:30. I never anticipate keeping you till 9:30. I don't want to stay till 9:30. And actually for most of these, since we're only doing one chapter, it actually works out pretty well for the rest of the class. So, I think honestly, 8:30 is going to be the latest we're going to get out most nights. So you'll get one sheet of paper. For your final exam, you get one sheet of paper. And I'm going to give you a copy of the Z table.
Oh, that's nice.
So, well, that's for two reasons. One, yes, I'm being nice, but two, I then know all your answers are going to be based on because I'm giving you the numbers you're going to use. So I don't have any issues with right. I don't have any issues with rounding errors or anything like that. This is the numbers you have to use. So, yeah, but we only have 2 weeks left of class.
2 weeks left.
Yeah, 2 weeks left of class. We have chapter 10 and 11 next week, 12 final. That's it. So, yeah. Told you guys were crazy. Huh? So the 9 through 12 test is actually online. It will be posted. Because I have to do chapter 12 before you guys really can do it. So it'll be online. It won't be due until actually after the final. It'll be due the 8th. So I would do it and then do the review. Like, it's just the way that it works because I don't have time. Like, I would have done it after I did chapter 12 that day, but like, I didn't think that was kind of fair. So, and I don't want your grade based on 2 tests and a final exam, basically. So, kind of 3 tests. So, it'll be on Hawks. So you'll have it, but it'll be due the 8th, the same day all the homework and everything else is finally due on the 8th. Yep. It is. All right. Other than that, any questions? Okay, go home and do your test. Congratulations. You get to go home and go to bed.
So we did all of 9 today, right?
Yes.
Monday, 10 and 11 or
10. It's 1 chapter a day.